Okay, so today we are going to learn about magnetism. Any idea about magnetism?
Um, yes, sir. There are like electric magnets and the magnetic fields are there. The magnetic length,
But
the motion
but
of
what
the
is
arc.
what is magnetism? What is magnetism?
Yeah, like the ability of magnetic field to affect things or like to attract or repel.
Okay, that means it's a property.
Yes, sir.
Okay, it's a property to attract magnetic materials. Okay,
Yes.
so there are two type of magnets. One is natural magnet, and another one is electrical magnet. Okay.
Yes.
So, in this chapter we will discuss permanent magnet and magnetic materials, describing method of magnetization and demagnetization, explaining magnetic forces in terms of magnetic field, and describing electromagnets and their uses. Okay.
Yes.
So, permanent magnet, you can see the examples like bar magnet. So, bar magnet is a permanent magnet, and what is that permanent magnet? When it is free to rotate. So, like if you hang it and if it is free to rotate, then it always rests in north south direction. Okay.
Yes, sir.
So, a compass needle is like a bar magnet. When it is free to rotate, it turns to point north south, and one point north, this is magnet's north. So, whatever uh, is towards north, so that is actual north. Okay. So, basically the permanent magnet is also a reference point for the directions as well. Okay. Like
Yes, sir.
nowadays there are mobile phones, but before mobile phones we have to go through magnetic compass.
Yes, sir.
Okay. So, there is a magnetic needle, so that shows the direction of north and south. Okay.
Yes, sir.
So, pointing roughly in the direction of the earth's geographical north pole, the other end is the
Yeah, I
magnetic.
can see the text. I can't see the text here.
You are not able to see the text. Oh, sorry, yaar.
Yes, sir.
My video was off.
I think the camera is off.
Yes. Yeah. Video is off. Okay. Now you are able to see.
Yes.
Okay. So, a compass needle is like a bar magnet. When it is free to rotate, it turns to point north south. One end point north. This is the magnetic north pole. Okay. Pointing roughly in the directions of Earth's geographical north pole. The other end is a magnetic south pole. Sometimes the north and south pole of magnet are called the north seeking and south seeking poles respectively. So, basically this is north pole of the magnet, and it is pointing towards the north pole. Okay.
Yes.
So, a freely suspended magnet turns so that it points north south. When two magnets are brought close together, there is a force between them. If we brought two magnets together, so what will happen?
They repel.
They repel. The same poles will be repelled. Like pole will be repelled, and unlike pole will be attracted towards each other. Like here, in example, we can see north pole is this is north pole, this is north pole, so they will repel each other. And here it is north and south, so they will attract each other. So that is basically the property of bar magnet or horseshoe magnet. Okay.
Yes.
So, like pole means both north, both south, and like pole means opposite poles, one north and another south. People often remember this rule more simply as opposite attract. Okay. So, since the north pole of the compass needle is attracted to Earth's north pole, it follows that there must be a magnetic south pole up there. Under the Arctic ice, it is easy to get confused about this. In fact, for a long time, medieval scientists thought that compass needle were attracted to the pole star. Eventually, an English instrument maker called Robert Norman noticed that if he balanced a compass needle very carefully, it is midpoint, it tilted downward slightly pointing into the earth. Now we know that the earth itself is a magnet. Earth itself is magnetized, rather as if there was a giant bar magnet inside it. So basically we consider that there is a giant bar magnet inside the earth. Okay.
Yes.
Now we will talk about magnetic materials and magnetization. So magnetization is basically a property of a magnet, okay, to attract or repel, to attract magnetic materials. So what is magnetic materials? So a compass needle is a permanent magnet. Like many bar magnet, it is made up of hard steel. You have probably come across another type of magnetic material called ferrite. Okay, ferrite is also a magnetic material. This is ceramic material used for making fridge magnets, and the magnets sometimes used to keep cupboard doors shut. So in cupboard door we also use that permanent magnet, okay, and sometimes in your geometry box also there is a permanent magnet fitted, okay.
Yes.
And even in your headphone, in your sound systems, there is permanent magnet used. So there are also small rare earth magnets in the headphone used with MP3 players based on elements such as neodymium. So that is another material, that is a magnetic material. So most magnetic material including steel and ferrite contains iron. So the commonest magnetic element for this region, they are known as ferrous materials. So ferrous materials are always attracted towards the magnet, okay.
Yes.
That means iron, there is iron in that material. So if a material contains iron, this is not a guarantee that it will be magnetic. Stainless steel is an example. It also have iron, but it is not, it contains a lot of iron, but magnet will not stick to it. Got it?
Yes.
So usually magnetic material are in an unmagnetized state and they must be magnetized. For method of doing this called magnetization are listed below. Okay. So what is magnetization? If a piece of metal may be stroked with a permanent magnet, by stroking it consistently from one end to other, never going in the reverse direction, it becomes magnetized. Okay, like we can see that this one. If we connect a magnet, let us say it is a ferrous metal, and we connect a magnet at this end, so this end also becomes magnetized. So it will be also behave like a magnet. Okay.
Yes.
So that the process is called as magnetization. Okay. It's a iron.
How does it work, sir?
Huh?
Is there a process to how it works?
Yeah, we'll see there. That is a property of magnetization. Okay.
Yes.
So if we connect north pole here, this end becomes south pole because it is attracting it. So that becomes south pole, and that becomes this will become the north pole. Okay.
Yes.
So yeah. So place the material in a strong magnetic field as produced by an electromagnet, it becomes magnetized. If we are in a strong magnetic field, then the magnetic material will also become magnetized. Okay.
Yes.
Place a long thin piece of metal so that it lies north south in the earth's magnetic field. Heat it. Where it cools, it will have been magnetized by the earth's field. So these are some examples of magnetization. How magnetization is happening. So alternatively, hammer a piece of material placed in a north-south direction and it will pick up the earth's field. When steel ships are made, they are hammered as the metal plates are riveted together. The whole ship ends up magnetized so that any compass on board will point the wrong way. The ship has to be demagnetized before it can set sail. Okay. So ship becomes magnetized once it is in the direction of north-south pole of the magnet, of Earth's magnet. Okay. So if sometimes that aligned with the Earth's magnet, so that also becomes magnetized. So that's why your ship is to be demagnetized. Okay. So magnetized materials are classified into there are basically two classifications. One is hard, another one is soft. What is hard? Hard means its magnetization and demagnetization is it takes time. Okay, it takes time.
Hard is needed for permanent magnet, right?
No, that has different uses. We'll study that. Okay,
Yes.
but like if it's a magnetic material and I just take magnet close to it and this becomes magnetized very fast, so that is a soft material. Okay, and if it is not magnetized very fast, then it's a hard material. Okay,
Yes.
so uses are different. Magnetized materials may be classified as hard or soft. So a soft magnetic metal such as soft iron can be magnetized and demagnetized easily. That means its magnetization, demagnetization is very easy. Okay. So what is hard type of material retains magnetism well. Even after removing the magnet, it is also magnetized for some certain amount of time. Okay. So that is a property of hard magnetic material. And what about soft? As you remove the magnet, it just demagnetized. Okay. So hard means retains magnetism well, but difficult to magnetize in the first place. It is also very difficult to magnetize initially. Hard steel, example is a hard steel, uses permanent magnets, compass needle, loudspeaker and magnets. Now soft one is easy to magnetize but readily loses the magnetism. So that is soft iron, coarse for electromagnets, transformer and radio aerials. So that is the use of soft magnetic material. Okay.
Yes.
So demagnetization is the reverse process of magnetization. Okay. So now we will see what are the methods to demagnetize. So first one is hammer the magnet. So when a magnet is placed in east-west direction and hammered, it loses its magnetism. Okay, rather than keeping in north-south direction, you just keep it in east-west direction and just hammer it, so it will demagnetized. Okay. This explains why the magnets used in school bags, school labs gradually lose their magnetism if they are repeatedly dropped and bashed about. Okay. So if magnet is repeatedly dropped, then it will lose its magnetism by some day. Second one is heat the magnet. If the temperature goes above a certain temperature, it will lose its magnetism. Third one is place the magnet in the field of an electromagnet that is connected to an alternating current supply. The magnetic field will vary back and forth, gradually reduce the current to zero. The magnet will be demagnetized. If you are keeping your magnet in an electromagnetic field, okay, so gradually this will be demagnetized. Okay. Now what is induced magnetism? Induced means, what is the meaning of induced?
Well, like it's caused, like it's added.
Induced means that two magnets are not touching each other, or one magnet and the material, they are not touching each other, but even if they are not touching each other, then it is also magnetized. So that is called as
Yes.
induced magnetism. So a bar magnet is an example of a permanent magnet. It can remain magnetized. Its magnetism does not get used up permanent magnets are made up of hard material, hard magnetic material, okay, because
Yes.
they have its magnetism a very long time. So permanent magnet can attract or repel another permanent magnet. It can also attract other unmagnetized magnetic material also. For example, a bar magnet can attract steel pins or paper clips, and a fridge magnet can stick to the steel door of the fridge. What is going on here? Steel pins are made up of magnetic material. When the north pole of a permanent magnet is brought close to a pin, the pin is attracted. Even if I have this magnet and I have pin here, so what happens? If I lose that pin, it will be attracted towards the magnet. Okay. So that the end of the pin nearest the magnetic pole must be a magnetic south pole. So that's why it is attracted towards north pole. Okay. As you can see into this figure. So this is known as induced magnetism. They are not touching each other before, just it was attracted towards the magnet. Okay. So the permanent magnet is removed, the pin will return to its unmagnetized state, or it may retain a small amount of magnetism. So steel pin is temporarily magnetized when a permanent magnet is brought close to it. Got my point? That means even it is not touching the magnet. So before touching the magnet, if it is kept inside its magnetic field, so that pin is magnetized. Okay. They are not physically touching each other, but before touching, it also behaves like a magnet. Okay. So closer to north pole, it will create south pole, so that they can attract each other. So this is called as induced magnetism. Okay. Okay, this is question for you. Two bar magnets are placed side by side as shown in figure 16.6. Copy the diagram and show the forces the two magnets exert on each other. State whether they will attract or repel each other.
They will attract, right?
Yeah. So that north pole will be attracted towards south, south will be attracted towards north pole. Okay. Okay, now one of the magnet is reversed, so that its north pole is where its south pole was. Draw this situation and show the forces of two magnets exerts on each other. Then the forces will be reversed. Okay. Iron is often described as a soft magnetic material. Many types of steel are described as hard magnetic material. Explain the difference between these two types of material. Explain.
So soft takes a shorter time, right, for it to get magnetized.
Yeah, to get it magnetized or demagnetized, it takes very short time, and hard one will get, it will take a lot of time to magnetize as well as in demagnetization. Okay.
Yes.
And why a permanent magnet should be made of steel rather than iron?
Because it's harder, right?
Yeah, it's you can say a harder magnetic material. Okay, so permanent magnets are made up of harder materials. Okay.
Yes.
Now what about magnetic field? We heard about this magnetic field, magnetic field, magnetic field. What is magnetic field?
It's like a force which affects any magnet within the area, right?
Yeah. So it is basically a force, we can't see it. Okay, it's an area in which that force is applied. So if you keep some magnetic material or a magnet into that field, so it will experience a force. So that is called as magnetic force. Okay. So magnetic field is, magnet affects any piece of magnetic material that is nearby. So we say there is a magnetic field around the magnet. So magnetic field is just a imaginary field. Okay.
Yes.
So you have probably done experiment with iron filling or small. Okay, if you keep that bar magnet like this on a table, and you just throw iron fillings around it. So what will happen? You will see this type of pattern. Okay. So the all of your fillings will be arranged in a particular manner. Okay. So if this is happening every time, that means that something is behind this phenomena. Okay. They are aligned in a particular line. So these lines in which they are aligned, so these lines are said to be the magnetic field lines. Okay. These are imaginary lines. Okay.
Yes.
Okay, we'll see that. So that is a magnetic field pattern of bar magnet is shown up by iron filling. The iron filling cluster most strongly around the two poles of the magnet. This is where the field is strongest. So you can see the bunch of sprinkles around two poles. It's very denser there. Okay. So that means it here at the poles they have very high magnetic field. Okay.
Yes.
So shows how we represent the magnetic field of a single bar magnet using magnetic field lines. Of course the field lines, okay. So now we'll talk about the direction of magnetic field lines. So basically they are aligned like they are emerged from north pole and they are going towards south pole. Okay. So basically this is the pattern in which your fillings are aligned.
So from north to south, right? So
Yes, from north to south always. Okay, you have to remember it. If you were place a tiny compass at a point in the field, it would align itself along the field line at that particular point. So you can see here, if you just keep that compass here, so it will align from north to south. Okay. So it would align itself along the field line at that point. So at every point, the direction of field line will be different. Okay.
yes.
Because and direction is always given by the tangent at field lines. Okay. Field lines come out of north pole and go into the south pole. So this thing you have to remember. They are coming from north to south. Okay. So that is all about the direction of magnetic field lines. Okay. Now, so this is another picture. From here north to south they are going, and this south is receiving the magnetic field lines. Okay. North is just emitting magnetic field line and south is just receiving it. Got my point?
Yes, sir.
Okay. In a single bar magnet it will look like this, from north to south, from north to south, from north to south, from north to south. If field lines are used to represent the magnetic field around a bar magnet, the attraction between two opposite magnetic poles shows up in their field pattern. The field pattern for two like poles repelling each other. Okay. So now strength. Lines close together indicate a strong field. So wherever you see the denser fillings in the experiment, so that was the strongest magnetic field. So line close together indicates a strong field. Okay. So we can also show the field pattern of two magnets attracting and repelling each other. Notice that there is a point between the two repelling magnets where there is a no magnetic field. Okay.
Yes.
Where is the diagram? Okay, this one. If it's a repelling magnet, then here in this field there is no magnetic field. They will not experience any magnetic field. Okay. So if we keep any magnetic material here, nothing will happen. Why? Because there is no magnetic field there. Okay.
Yes.
Okay. Plotting field lines. So plotting field lines will be from north to south. Place the magnet and iron fillings can show up the pattern of magnetic field around a magnet. Place the magnet under a stiff sheet of plain paper or clear plastic. Sprinkle fillings over the paper or plastic. Tap the paper or plastic to allow the filling to move slightly so that they line up in the field. You should obtain a pattern similar to that shown in the figure. Okay. So we can see it practically as well in lab. Got it?
Yes.
Okay. So an alternative method of doing this uses small compass. So through compass also we can plot that magnetic field lines. Okay. Wherever is the direction of needle, so that will show you the direction of magnetic field line. Okay, that will be aligned accordingly. Now electromagnets. Electromagnets sometimes or even many times magnets are made electrically. So that type of magnets are known as electromagnet, and that is very useful method of making magnet. Okay, because permanent magnet we can't increase the strength of that magnetic field, but here in electromagnets we can increase the strength of magnetic field. Okay, so how they are made up of? It is just a soft iron or hard iron. We take accordingly what type of magnet we want to make. So we just make some turns of the wire, copper wire, let us say it's a copper wire. Okay, so if we wrap some copper wire over that magnetic material, they are insulated with each other, and we just give a supply. Okay, like if you connect a coil with the battery or supply, so it will behave like a magnet, it will magnetized. Okay, so this is said to be electromagnetism. So this phenomenon is so known as electromagnetism. Okay, that means if current is being flown in a conductor, it will also create a magnetic field. That means electric field is creating magnetic field. Okay,
Yes.
so wherever current is flowing, there is also a magnetic field. Got it?
Yes.
So using magnetic material is only one way of making a magnet. An alternative method is to use an electromagnet. A typical electromagnet is made from a coil of copper wire. A coil like this is sometimes called a solenoid. So this type of arrangement sometimes is said to be solenoid. Okay. When a current flows through the wire, there is a magnetic field around the coil. Copper wire is often used because of its low resistance. Now other metal will do. The coil doesn't have to be made from a magnetic material. So this coil doesn't have to be made up of a magnetic material. Copper is not a magnetic material. Okay.
Yes.
So that coil is made up of copper wire. So the coil doesn't have to be made from magnetic material. The point is that it is the electric current that produces the magnetic field. So
Yes.
until unless your current is flowing into this coil, so there will be a magnetic field. Got it?
Yes.
Okay, now you can see the magnetic field around a solenoid is similar to that. So your solenoid will behave like a bar magnet. Got it? So one end of the coil is north pole and the other end is south pole. So we'll see into that figure. Next one, this one. Okay. So this is basically becomes north pole and it is becoming south pole. So wherever current is entering, so that if current is entering towards up, so that will be your north pole. Okay. So it will also depend upon the direction of current. So if you change the direction of current here, means you connect the battery in opposite direction, so that will become south pole and that will become north pole. Got my point?
So, does the current flow out through the North Pole?
So that means you have connected battery like this, okay, because current is entering through this wire, so that is current in. So current in always give you north pole, okay.
Yes.
And if we connect the battery like in opposite direction, that current is being flown into this, so that will become north pole. So from which end your current is entering, that will be your north pole. Got my point? Okay, very good. So that is an example of solenoid. So you can see the magnetic field around a solenoid is similar to that around a bar magnet. One end of a coil is north pole and other is. So there are three ways to increase the strength of an electromagnet. Because current is being flown there. So if we increase the current, then its magnetic field will also increase. Okay? If we increase the number of turns, then also magnetic field strength will be increased. Okay? So first one is the current. So if you increase the current, that will increase the magnetic field strength. Increase the number of turns, so magnetic field strength will be increased. And add a soft iron core, because soft iron core is magnetized easily. Okay, so that will be a heavy magnetic field if you use soft iron core. Got my point?
Yes.
Okay. So like this is an example of electromagnet. In a scrap yard, a steel object or pile of scrap can be lifted and moved, then the current is switched off to release it. Got it? So first we make it magnet by using some current. So it behaves like a magnet, so every magnetic metal will stick to it. And then wherever we want to drop it, we just switch that current off. So it will demagnetized, and whatever is the magnetic metal, that will be dropped there. Okay?
Yes.
So that is the use. So an iron core becomes strongly magnetized by the field, and this makes the whole magnetic field much stronger. Now the electromagnets have the great advantage. So what are the advantage over that permanent magnet here? Can you tell me?
So yeah, the magnetism, the strength of the magnetism can be changed, right?
Yes.
Yeah, you can make it stronger or weaker.
Okay. And any other thing?
And it can be demagnetized at will.
Yeah.
If you want, you can
Because
demagnetize it.
you can't demagnetize permanent magnets, but you can you can demagnetize the electromagnets. So that is the basically main use. Okay, what is another use? What is another advantage?
It can be used in electrical circuits. It can be used in like relays and all of that.
Yeah,
You can use it in electrical circuits.
yes. Okay,
Yes.
so that is most important question. It may be asked in your exam as well.
And also any material can be used, right? So it only depends on the current, right?
Sorry?
And also any material can be used, right? It only depends on the current, right?
But it should be conductor.
Yeah, but like any conductor is okay. But for this permanent magnet, only like steel, there are very hard metals required.
Yes.
But for this, any conductor is okay, right?
Yeah. So electromagnets can be switched on or switched off. Electromagnets are also used in electric doorbells. Doorbell is another example of electromagnet. If you just keep on pressing, what will happen?
The sound will come.
If you just electric doorbells are just pressed once only, what happens?
The sun will come and go.
Yeah, so the hammer whatever is it is magnetized, so that will impact that plate. Okay, so sound comes. Now if you are pressing continuously, so what will happen? That hammer will not demagnetized. Okay,
Yes, sir.
even you keep on pressing it, so it will just ring once, it will not ring twice. Why? Because the hammer is attached to the plate and it is not releasing. So the sound was because of the hammer striking the plate. Okay.
Yes, sir.
And the loudspeaker also example of electromagnet. What happening if you just you can see the treble and bass. You can increase treble, you can increase bass. So what is happening? You are just increasing or decreasing the frequency. Okay. So treble is the higher frequency and bass is the lower frequency. So if you are increasing bass, that means you are going lower to the frequency to pass.
So what is bass?
Bass means dum dum sound like. Okay. So that is bass. Bass, you can say bass.
And what's travels?
Actually, nowadays we don't have that stereo systems which have treble and bass. Okay, nowadays there are jazz, pop and all
Oh, yes.
frequency settings,
Yes.
isn't it?
Yes.
So in our days there was two different treble and bass, so we can adjust that, the frequency which is to be passed. Okay.
Yes, sir.
So that is the main difference. So we are just adjusting the frequency to pass once we adjust treble and bass. Okay.
Yes.
So it is used in electric motors, it is used in relays and transformers. Okay, now the question is, draw a diagram to show the field pattern between two magnets of equal strength whose south pole are placed close together. So south pole are placed close together. There are two magnets.
Both are close together, then it will repel, right?
Yeah, it will repel, but electric field line will go from north to south. Okay. Describe how an electromagnet could be used to separate copper from iron in a scrapyard.
Yeah, the electromagnet will attract the iron.
Yes.
The
So
copper will be left.
yeah, so that is the very good example to make it filter. Okay.
Yes.
Now the field around a solenoid, I already discussed you. Solenoid also behaves like a bar magnet, like now north and south pole. So when an electric current flows through a solenoid, a magnetic field is produced inside and outside the coil. This field is similar to that around a bar magnet. Okay, there is no difference. So whatever is the electric field in bar magnet, like in bar magnet, so that will be the same. Okay.
Yes.
Okay. So one end of the solenoid is the north pole and the other end is the south pole. Field line emerge from the north pole and go into the south pole. The same thing, whatever we were just plotting in bar magnet from north to south, so that will be the same thing. Okay. The field lines are closest together at the pole, showing that this is where the magnetic field is strongest. So at the pole, magnetic field is strongest. The lines spread out from the pole, showing that the field is weaker in these regions. Got it?
Yes.
So the same thing, because it will behave like a bar magnet. Okay, now chapter I think it is completed. Yes. So there are some questions. Do you want to go through that?
Yes.
Sketch a diagram of the magnetic field pattern of a solenoid.
Yes, that was the question I had in sir. Like, how will the solenoid actually work the magnetic field? Like, I was going to ask you that.
See, whenever there is a current in a wire,
Yeah.
so if current is there in a wire, so that will produce a magnetic field around the wire. Okay, every time. So here in a solenoid, it is a bunch of turns. Okay.
Yes.
So what it makes? It is making magnetic field stronger. Got it?
Yes.
And
So, but like, how would the diagram look like, sir? Can you just draw the thing? What would it look like?
okay. So if this is your solenoid and it is connected like this, so current is being flown into this. Okay.
Yes.
So that will behave like a north pole. As you switch on the supply, that will behave like a north pole and this will behave like a south pole. So your magnetic field lines will be going like this. Okay.
Yes, sir.
The same way was that the bar magnet. Okay.
Okay, so from north to the south.
Yeah, from north to south. How would the pattern change if the current through the solenoid was reversed? So if
Pattern will be opposite.
yeah, pattern will be opposite. So poles will be changed. North will become south, south will become north. Okay?
Yes. So it will flow from south to north.
Sorry?
So will it flow from south to north then?
No. Magnetic field,
Because the direction will be reversed, right?
yes, magnetic field lines will be always from north to south.
So the northern, the position will change, right? Only that.
Yes. Poles will change. So earlier they were going from, see, if you change the direction of current, earlier it was north to south, earlier it was like this. Okay. If you change the direction of current, so that time it will be south, it will be north. So magnetic field line will go through this path. Okay.
Yes.
So only the direction is reversed, path will be same.
Yes.
Path is not getting changed. Okay. Now fifth question. After fifth, no question is there. Okay, the now end of chapter questions. What is that? 16.1. Okay, now figure 16.11 shows four permanent magnets arranged to form a square. Copy the diagram and indicate which pairs of magnet will attract one, another and which will repel.
Yeah, the 2 and 3 will attract, right?
Yes.
2 and 3, and then 1 and 4.
Yeah. So 1 and 4, 2 and 3 they will attract each other. But 1, 2 and 3, 4 they will repel each other. Okay.
Yes.
Okay. So now you have to draw a second diagram in which the four magnets are arranged in a square so that each magnet attracts the two other magnets to which it is closest. Just reverse the direction of the magnets. Okay. So that will be another combination they want.
Yes.
Okay. Now this 16.2.
Strength of electromagnet, it can increase in the current, or like putting a more conductive material or decreasing the resistance.
Okay.
Yeah.
And number of turns can be increased.
Yes.
Okay. An electromagnet can be switched on and off. Suggest one situation where this would be an advantage over the constant field of permanent magnet.
Yeah, like doorbell.
Doorbell, yeah. It's a great example. We use it regularly. What is the difference between a hard magnetic material and soft magnetic material?
The hard material takes a long time to magnetize and demagnetize, and it forms permanent magnets.
Yeah.
While soft material takes short time, but it cannot form permanent.
Yes. So now explain which you would choose for a permanent magnet.
Steel.
Yeah, hard one. Okay, hard magnetic material.
Hard ones like what? Like steel and what else?
Yeah. Explain which you would choose for the core of an electromagnet.
Yes, sir, like steel and which one else, sir? So like, can you write like something like copper or something like that?
No. Copper is not a magnetic material.
Then sir, steel and what else?
Just we have to Google it. Hard magnetic materials. Actually, there are some alloys.
So like what? Like nickel?
Aluminium, nickel, cobalt.
Oh, yeah. Yes.
Okay. Copper, nickel, ferrous.
Yes.
Okay.
Yeah, explain which is the core of electromagnet. The core of electromagnet
Is a soft.
like iron, something like that, right?
It will be a soft material.
Yes, like iron.
Okay, iron.
Because why soft? Why cannot be hard?
Because it will not demagnetize after even switching off the magnet. Okay. And it will not switch on very fast.
Yes.
So that will be its main advantage. Solenoid has a magnetic field similar to that of a bar magnet. Copy the diagram in figure 16. Okay. Where is that question? 16.4. Okay, figure 16.12 for question 16.4. This figure is to be used for question.
This is question 16 first.
Where is 16.12? Okay, copy the diagram in figure 16.12 which shows a bar magnet and solenoid arranged so that they repel one another. Label the poles of the solenoid and okay, this is bar magnet, this is solenoid. So you have to arrange it. Now where will be the north pole and south pole of this solenoid?
North pole is where the upwards arrows going, right?
Yes. Yeah. So that will be north pole. That will be south pole. So copy the diagram in figure 60 which shows a bar magnet and a solenoid arranged so that they repel one another. Label the poles of the solenoid. So you have to reverse it. Okay?
Yes.
Because it is north and south. Add field lines on your diagram to represent the magnetic fields of the bar magnet and the solenoid. It's very simple. Okay.
I'm sure it transfers from south to north, right? No, sorry, north to south.
Every time it will be from north to south.
Yes, you got it.
Okay. Is there any doubt till now? Okay, so in the next session we'll go through static electricity. Or you want some other chapter?
And also we did some electricity last time. We did it.
Okay.